So I'd like to start off with some overview of what we'd like to accomplish, and then go through a couple atmospheric transport modeling code systems, some mathematical equations I'll try to go through quickly, and then some of the preliminary effort we have gone through in benchmarking those code with volcanic ash data. This is the best we have been able to do during the summer, and as Milton indicated, very recently we obtained access to radionuclide data, and we have begun to do some analysis, but release of public discussion of those results requires interagency approval. We didn't have time to go through State Department for the approval, so I won't be able to show any of the actual results, unfortunately, today. Okay. So as Milton indicated again, we just got access to roadmap, ground-based nuclear detonation detection roadmap, and there are a couple important objectives indicated. First, we need to develop accurate enough atmospheric transport modeling system that can track radionuclide releases, and then also at the same time to assess uncertainty in our ability to detect source, location, and magnitude. So these are some of the really ultimate goals that we'd like to go into. So we would like to certainly look at and compare two ATM code that we've been using and cross-compare and try to get some idea on the accuracy of these code. And ultimately, we'd like to be able to coordinate with seismic and infrasound data. This would be obviously ultimate goal of what we are trying to do. As I advertised, I'd like to quickly go through mathematical foundations of these code systems. And this is based on primarily advection and diffusion of some kind of fluid, primarily air, with radionuclide considered as tracers attached to the fluid. And so here we are looking at U as the velocity of the fluid, and the K diffusion coefficient. We are representing advection and diffusion equations. Alpha and chi, by the way, is the radioactive radionuclide material nuclide concentration. And alpha represent departed scavenging as well as radioactive decay and production. And we have the source, of course, okay, radionuclide source. And often this Eulerian form of the advection diffusion equation is converted into Lagrangian form by combining this advection term with time derivative. So we have somewhat of a simpler form. But also what is interesting is in order to get some idea on quantifying source, we'd like to go through adjoint formulation of this advection diffusion equation. This adjoint formulation has been in use in reactor physics, nuclear reactor physics, for quite a while, half century maybe. I remember working on some aspect of this maybe close to 40 years ago. And however, here what we are looking at is this. R is the reaction rate of the detection system, and H is the detector response, maybe cross-sections in efficiency of detector and so on included. And we represent this in terms of adjoint operator. L is the operator representing all of this. We have L dagger, and we have chi dagger, which is adjoint to the physical radionuclide concentration. And by going through inner product and taking care of boundary conditions properly in the integration process, we obtain this expression for the adjoint concentration chi dagger. And the only thing is something that went in going from PowerPoint to PDF, but there's a bar here indicating that we changed the sign of this derivative, Lagrangian derivative. Otherwise, everything really remains the same. the beauty of this adjoint approach, sometimes at ATM description, this is called backward model, but it's really adjoint formulation, is that by calculating adjoint concentration, we can account for contribution to multiple sources to a detector. Otherwise, you have to run large number of forward calculations to represent individual sources. But through adjoint formulation, you run one case and account for contribution from large number of sources simultaneously. That's the beauty of adjoint formulation. So the way we, again, I forgot to mention that we had a collaboration with Dr. Paul Esslinger from PNNL through help with Daniel Stevens, yes, here, and Ted Boyer. I appreciate all the effort that you made on our behalf. And so Matthew Krupkale, one of our students, did internship under Dr. Esslinger. I couldn't use the first slide as I began to talk. Anyway, so the idea behind the source estimation through Bayesian formulation goes something like that. As I indicated, by using the adjoint concentration, we can come up with the reaction rate at associated to multiple sources. So we come up with initial estimate of the source, and we'll describe a little bit how we went through forward and adjoint combination to get an estimate of the sources with the synthetic databases we use. And so we come up with the relationship between source and the reaction rate. Here we have, and then go through Bayes' theorem. So we begin with the initial estimate and use this function, which is called likelihood function, and come up with update estimate of source based on the use of the reaction rate we calculate with the adjoint estimated transport calculation. So this is the basic idea behind synthetic estimation of the source intensity and location and so on. Again, as I said, we use two different code systems so far, HYSPLIT and FLEXPART, and they are both based on Lagrangian model, and it has both of them have capability to forward and adjoint modeling, and they are used by different organizations, PNNL, Paul Esslinger used HYSPLIT primarily with Oceanic and Atmospheric Administration ages. And we also tried FLEXPART at Michigan. This is used by CTVDO and some of the weather prediction systems and so on. Okay, so we try to first benchmark FLEXPART code so that we know we are using the code properly. So we tried a few things, but I will move forward quickly. So we followed 3 days of motion of volcanic ash that was released in a volcanic eruption in Iceland, and we followed through the motion of the ash using the FLEXPART code. So the 3-day simulation. And this is benchmark data, but we are using two different versions of the code and so on. So we are not sure we will have good enough benchmarking. But at the end of 3-day simulation, we have quite good agreement with the benchmark data. So we are pleased with it. And HYSPLIT is another code that PNNL uses. We made the initial stab at, again, benchmarking with the same volcanic data, but we ran out of time more or less. So we will have to look at it a little bit. And possibly these codes, both of them require a huge amount of computer storage space, approaching terabytes and things like that. So this is one of the difficulties we deal with atmospheric transport modeling, as we realize. So anyway, there are some differences, but we are making effort there. And this is what Matthew worked with Paul Esslinger at PNNL during the summer. So here we simulated And Matthew's got poster board that explains some of these in more detail if you're interested in it. We have two initial sources, one here in Idaho, the other one in Kansas, do I remember correctly? Right? And this is the point source we started off and performed forward calculations and took measurements at 11 stations. Based on that, we like to move backward in adjoint calculation and try to reconstruct the source. And these are the probably density function plots. And this is actual source release time for two sources we had, and this combined release time and the magnitude and so on. So we are doing fairly well, not perfect, but I think we are moving along okay. And now I'd like to just briefly mention that, as Milton indicated, we just got access to 80 IMF radionuclide data, but only part of it, US only data. There are 80 IMS radionuclide data stations, but we've been allowed just US alone. So the 11 stations distributed over continental, contiguous United States, Alaska, and Hawaii. Which one is Hawaii? 10, this one, okay, Guam, and then these are in the Wake Island and so on. So we have basically iodine and cesium data for 11 IMS stations, but we just obtained this morning xenon data for, I think it's just 4 stations, and I do not understand why not all 11 stations US claims cannot produce radio xenon data yet. And even that preparation of data took a special route. So we are not sure how conveniently we can process data and actually perform simulation. That's about all I had, and then future tasks, as I indicated, we'll move forward with doing better job with a lot of things that I've discussed already, with the purpose of satisfying some of the goals of the roadmap we discussed. Okay, I'm doing okay with time? Yeah.
Well, I showed this graphic actually in the previous presentation here, so I'll just run through it. You're looking toward the southeast at the Korean Peninsula.